Good evening. Welcome to the second week live interactive session for the NPTEL course Transition Metal Organometallic Chemistry from Principle to Application. So I was little bit late because of this my computer issue. So without I will wait for another 1 2 minute 2 3 minute for if anybody wants to join. Otherwise I will start discussing the today's session through this problem solving with the different question and different types. I'll wait for another 2 3 minutes, then we'll start the student session. If anybody has any question, you can ask me regarding the last session or anything regarding this week content. So in this week, that is the second week of this course, we have discussed different types, that is we have classified this organometallic compound in three classes: class 1, class 2 and class 3, based on their total number of valence electron. How to calculate the valence electron for different types of ligand with different metals like 3D, 4D, 5D with using the neutral method we have already discussed in the last session. Also we have discussed how many electrons contributed by different types of ligand to the metal center in regarding the counting of total valence electron when we are using neutral methods. So neutral method are more convenient, or we can say that it is more easy to calculate the total number of valence electron regarding the other method, that is the ionic method. Ionic method, anyway you need to find the charge of the metal, then the charge of the ligand, then calculating and neutrality, that is the difficulty. But in neutral method it is very easy to calculate the total valence electron for the metal complexes. So regarding the total valence electron of the metal complexes, we classified metal complexes, that is organometallic compounds, in three classes, whereas it's a class 1, class 2 and class 3. For the class 1 complexes, it doesn't obey the 18 electron rule. So that means it have valence electron, any number of valence electron, 16, 17, 18, 19, any number of valence electron. For the class 2 complexes, it valence electron should not exceed number 18. That is, the valence electron may be 18 or less than 18. And the class 3 metal compounds or organometallic complex having particularly 18 number of valence electron. So depending upon the energy gap with different metal systems, we have classified these metal complexes. For the class 1 metal complexes, is the electron count is generally the less than 18 or greater than 18 or sometime 18. That is generally follows by the 3D transition metal complexes like titanium, vanadium, chromium or nickel. Nickel like nickelocene or nickel ethylene diamine ulthrice 2 plus, these types of complex exist the 18 valence electron, whereas the manganese tetraacetate or vanadium Cl6 2 minus having the 13 valence electron or 16 valence electron, that is the less than 18 valence electron. So for the class 2 metal complexes, another so simple class 1 metal complexes is considered for the 3D metals only. For the class N, it has the T2G and EG energy gap is smaller. So both the level is equally populated. For the class 2 metal complexes, we have our metals generally for the 4D and the 5D, especially in their highest oxidation state. Here T2G is essentially non-bonding and occupy the 0 to 6 electron, whereas the EG star is strongly anti-bonding and no longer available for occupancy. Now the energy gap now which we are talking about for this class 2 type, because of the 3D metal, 4D and 5D metal complexes, from our idea of crystal field theory, we know that for these metal complexes the energy gap between the T2G and EG is much greater compared to the 3D. So these all complexes having the 18 valence electron or less than 18 valence electron, because the EG level, because of highly anti-bonding character, we cannot exist. So and I will show or discuss with the molecular orbital diagram when we will discuss the questions. So this I am giving a general idea for class 1, class 2 and class 3. For class 3 metal complexes, these metal complexes can be any metal, 3D, 4D, 5D, but these depends on the ligand, that is the ligands attached to the metal. For class 3 metal complexes, we have generally our pi acceptors ligands such as CO, that is carbon monoxide, olefins, that means alkenes, etc., which PF3 which have the strong pi acceptance property. So depending on this, we have here EG star is also strongly antibonding and remains unoccupied, but T2G star is quietly populated. So depending on this, we have for the class 3 only 18 valence electron. So this is the, and then with the there is the classification of the organometallic compound, and after that we have discussed the property of the ligands, and also the electron. We have also discussed the types of the ligands, that is the sigma donor ligand and then sigma alkyl compound, and their preparation with different method. So this is the main overall content for this week 2. So by solving the different questions, and I will start discussing the different problems um, for this week, and then I will explain how they are solved. At the end of this problem solving session, I will try to discuss some another important. I will pick up some important topic from this week, and I will discuss in more elaborately. So without wasting time, just go to the PPT to solve the different types of question for this week content. If anybody has any question regarding this session, you can directly ask me anytime. Also, I will request everyone to please post your doubts in the discussion forum. If you have discussion forum, questions will be directly answered by the um, professor and our team members. So if you have any doubt, you can directly ask your question. So discussion forum question I will try to answer as early as possible. So without wasting time, let's go to this today's uh, problem solving session. Now I think my screen is visible.
Yes, sir.
Okay, so welcome again to the week 2 problem solving session for the course Advanced Transition Metal Organometallic Chemistry from Principle to Application. So as we discussed this briefly at the starting of this course, that the different classes of organometallic compound, and we will also discuss with details the MO diagram and how we classified these three classes for class 1, class 2 and class 3, depending on the energy difference and electron filling of this compound with using the simplified MO diagram. So as per our question, the maximum number of valence electron that for a class 1 type complex can accommodate is
22, sir.
yes, so 22. So for maximum number of valence electron, and what can be the least, that is the lowest number of valence electron for these class 1 complexes, that is the maximum. Yes, the correct answer is 22. But what can be the lowest?
For 6 orbital, it will be 12.
Yes, it will be 12. So to understand this, we need to consider our molecular orbital energy diagram. I will draw very quickly and show how this is discussed. Any other question from this regarding this class 1 type compound? How it is going to 22
Sir,
or 12?
So we discussed that class 1 compounds are mainly of 3D compounds.
Yes.
Sir, even the strong when the ligand is in strong field ligand, we also have these type of class 1 compounds, or we shift to the, if it follows the 18 electron, we shift to class 3 compounds.
Yes. When we
Okay.
that's why we make another classes instead of class
Oh,
1 and class 2. Class 3 complexes are mainly for the we based on the ligands. When we have our strong field ligand, as for example CO and alkene complexes, that is the olefins or PF3, any strong field ligand, so then the you know that from the CFT that the pairing of electron is facile and it will going to the 18 electron rule. So the 18 electron rule, that is the specified valence electron for um, this organometallic compound, we having 18 number of electron, we have in classified as class 3, that is a special class, whereas the class 1 and class 2 we have don't we don't have any particular number of electron. For the class 1 we have any number of electron, and for the class 2 we are stopping at 18, so that the total number of valence electron cannot exceeds 18. Is this clear?
yes, sir.
Okay, should I discuss the MO or we?
Yeah, yes, sir.
Okay, so for our metal orbital we have our 6 orbital from the ligand, and we have our 5 d orbital, and we have our 1 s orbital and 3 p orbital. So if we have for this is for the class 1, this is for the class 1, and we are only considering here the sigma donation from the ligand. As far we say that when we are considering the pi donation arises from the strong field ligand. So class 1 compound always should contain the ligand which is weakly donating, that is the weak field ligand. So here, as per our knowledge, we have already know that we have our here 6 electron, that is the 6 orbital.
Yes, sir.
What are they? A1G,
EG T1U,
T1U. Very good. And what will be our anti-bonding orbital here?
EG star.
Eg star. And what will be the delta O?
Sir, so that will be a non-bonding orbitals, and the
Non-bonding.
delta O will be between T2G and EG star.
Yes, this T2G and Eg, it will have a delta O. So as we have that, I will not draw the other one, that this is the other part, because that is no, we have already seen during the lecture videos. So here that this orbital has 6 orbital, so 6 orbital can be filled for the 6 ligand. Okay, that is a 6 ligand electron, and 6 ligand electron, that will be 12. When the metal does not contribute any electrons, the least number of electron will be 12, and if we have this all are filled, then we will have this, this is
When
6.
metal contributed more to non-bonding.
Yes, if the maximum number of electron we are talking about for this question. So this one and this one all will be filled, right?
Yes, sir.
So 6 plus 3 plus 2, total
22. Electrons will be 22.
yes. So electron will be 22. So total number of electron will be valence
22,
electron
sir.
equal to 22. So any other question from this?
No,
Here
sir.
we are only talking about the our weak field ligand. So for the weak field ligand, this delta O value will be less. For that, we can feel that Eg star level also. Okay. For the
Yes, sir.
class 2 type metal class 2 type, if we are considering the class 2, then class 2 is for which metals?
4D and 5D metals.
Yes, for 4D and 5D delta O. So if I write delta O class 1 and delta O class 2, which will be greater?
So for delta 2, because 4D and 5D always have a strong field ligands.
No, we are not discussing the ligand effect. We are only have our 3D metals and our 45D metals. So why the 4D and 5D? So delta will be greater for class 2, right?
Yes, sir.
So, so when we are discussing, no ligand is considered for the class 3 only. So for the class 1 or class 2, we are classifying these two on based on the metal, that is 3D
Yes, sir.
metal and 4D and 5D metal. So for the 4D and the 5D metals, these orbitals are deeply seated, like the F contraction and all. So the energy gap between this Eg and T2G and Eg star for the class 2 is very much, that is the greater. So filling of the electron will be up to this Eg level only. Okay, so 6 plus 3, total 9 orbital is available, only available for the class 2 types of metal. Is this clear?
Sir, can you repeat why the delta O is greater for 4D and 5D?
For the 4D and the 5D orbital, they are large in size, right? Compared to 3D,
Okay, sir.
you know,
Yes, sir.
because of as the n value increases, the orbital size increases. Okay. So
Yes, sir.
when we are considering about any field of ligand, mainly weak field of ligand, so the interaction for these weak field of ligand or whatever field of ligand, their interaction will be not strong enough, and that will have the electron, means the separation between the two energy level will be more. And for the that's for 4D and 5D orbital, T2G and EG have delta O value greater, delta O value more than that 3D. So that's why, so these EG will be mainly have a non-bonding, and these will not be available for filling of the electron. That's why a non-bonding, no, this could be strongly anti-bonding. So for that EG will not be available for having the electrons because of the high energy gap. You can find it more
Okay.
details in the CFT chapter, where we are considering the metals based on this delta O value. So for that, only up to this T2G level will be available for the electrons to be filled. So that's why the 19 is 9, that will be gives 2 electrons, so 18. So that's why class 2 types of metal only have the 18 electrons, and it will
Okay.
not exist 18. Okay.
Yes, sir. Yes, sir.
So is this clear why that class 1 has more than 18 and less than
Yes, sir.
18,
Yes.
and the class 2 have up to 18? Because of this
Yes, sir.
delta O, only remember the delta O. For the delta O value for the class 2, that is for the 4D and 5D metals, is very high, and because of this high delta O value, the Eg star is strongly anti-bonding in nature, and it is not available for bonding, so electron can't go to this Eg level. So filling of the electron can only occupy up to the Tt2G level under normal condition. So that's why we are stopping the class 2 metals or class 2 organometallic complex up to this 18. It cannot go beyond 18, but for the class 1, delta O is smaller, Eg level can be occupied, and we have more than 18 number of valence electron. Okay, I think it is clear.
Yes, sir.
Okay, now this is a very easy question which also I have discussed in last session more detail. The valence electron count of titanium in TiF6 2 minus. First tell me what is the correct answer. So titanium is a 3D metal, right? And here
Yes,
we
sir.
will use
D2.
neutral method. So total number of valence electron will be
Sir, 12.
yes. So, so E has 3d2 4s2. Total number of electron is then 4. There is a d4 system. Then F will contribute 6 electron. As we have seen in last lectures also, that the halogen will contribute 1 electron in the neutral methods. So it will be 6, and it has a negative charge. For the negative charge we have to add electron, and for the positive charge we have to just subtract the number of charge. So for the negative charge it is we have to add. So, so total number of electron will be 12. So for this question 12 will be right answer. Okay,
Yes, sir.
going to the next question. Yeah, this question is what I am discussing for the first question. So it is saying that the splitting of delta 0 between T2G and EG orbital in class 1 and class 2 type organometallic complexes varies as. The splitting of delta 0 means this separation between T2G and EG. So this varies as for the class 1 and class 2 type organometallic complexes varies as. So delta 0 of class 2 is more than delta 0 of class 1. Delta 0 of class 2 is less than delta 0 of class 1. Eg star is highly antibonding in class 1. Eg star is weakly antibonding in class 2.
Delta 0 of class 2 is more than delta 0 of class 1.
Yes, and why it is we have already discussed, because of the 4D and 5D metals. This is the only answer. Yes, option, the which option is correct?
So first one.
Yes, first one. Is this the only option which is correct here?
So yes, sir. Yes, sir.
Okay, yes, this is the only option which is correct here. Another option, like option 2 is obviously incorrect. Here we have the 3 and 4 option. So here it is saying for the 3 option 3, Eg star is highly antibonding in class 1 and Eg star is weakly antibonding in class 2. So these two are wrong, right?
Yes, sir.
So Eg
The
star,
highly antibonding be in class 2.
yes, Eg star is highly antibonding in class 2 and it is highly antibonding in weakly antibonding in class 1. Okay, any other doubt?
No, sir.
Okay, next question is also for the valence electron count for palladium in palladium Cl4 2 minus. It has, what will be the number of valence electron? What will be the total number of valence electron for PtCl4 2 minus? This is like same na for TiF6 2
So
minus.
for
What will, let me tell the
so
what will be the electronic
16
distribution for palladium? Palladium is
4d10
which group?
says in zinc
What? Palladium in? I have already
nickel
written
group.
it. Yes. Nickel. Do you have periodic table?
Yes, sir.
Yes. Please see it, and you should, at least you should remember the periodic table for transition metal, P block and S block. F block is not required for now because we are not discussing anything from F block element. So but the S block and P block and the transition metal we need to remember. Okay, so this is the palladium and the nickel group, nickel, palladium, platinum. So for the nickel, this is cobalt, rhodium and iridium, and after nickel what is it? Is copper, silver, gold. Okay, this is 3D, 4D and 5D. So and then comes zinc, cadmium, mercury. Okay, so this is D2, D8, 4S, so 4D2, 4D8 and 5S2 for palladium. Okay, correct. So this is a
Yes, sir.
B10 system. So for the 10 system it has 10 electron plus chloride. For the chloride how many electrons?
4, sir.
4. And for the negative charge it will be
Plus 2.
plus 2. So total number of electron will be
16.
16. So option C will be correct answer, right? You need
Yes,
to
sir.
remember like periodic table because in the exam it will not provided. Okay, so you need to
Yes,
remember
sir.
at least some regular metal complexes like palladium, silver, rhodium, and obviously the 3D metal like from scandium to zinc. Okay, other metal is not that much important, but at least 3D metals and for the iron group, cobalt group, nickel group, copper, zinc, this group, like group means from cobalt to iridium, nickel to platinum, copper to gold and zinc to cadmium, like way you need to remember for this transition metal. Okay, going to the next question. Next question is again on the delta O value for class 1 and class 2 and class 3. It is saying that the splitting of T2G and EG delta 0 in class 1, class 2 and class 3 type organometallic complexes varies as.
Delta O value of class 1 is the least and the delta O value of class 3 is largest.
So delta 0 value for the class 1 is least, that is option A, right? Option A will be the correct answer. And delta O value for the class 3 will be largest. You are saying that, right?
Yes, sir.
Okay. For this question we have two options which is correct. So option A, that is the delta 0 value for the class 1 is least, and option D, that is the delta O value for the class 3 is largest. Very good. These two option is correct option. Next question is another question like for the electron count. What will be the total valence electron count for this vanadium? So vanadium is also a 3D metal. We have scandium, titanium, vanadium, chromium. So vanadium is 3D3,
3D3,
4s,
4s2.
4s2. So what is this? Is a D5 system. Okay. So what will be the then total number of electron, valence electron?
18 electron.
18. Okay, then let me count it. Okay, let me count it then. So this is 5, 5, and what will be the contribution for CO? 6, 6 into
2.
2, and then for the negative charge it will be
+1.
sorry plus 1. 5 plus 12 plus 1, total is 18. So option A here is the right answer. Okay, this question is very interesting. The geometry and the coordination number of nickel in NiCN4 2 minus respectively are. Okay, with addition to this also count the total valence electron for this for this complex nickel. The geometry and the coordination number of nickel in nickel tetracyanide 2 minus respectively are. That is the geometry and the coordination number. What will be the answer for this?
Square planar, the coordination number will be 4.
Okay, that means which option is correct?
C.
Option C. Very good. So option C. And what will be then? Tell me the total valence electron count.
So it will be 16.
So nickel in is which group? D8. That is 3T8 4s2. That is total 10 electron. So 10 plus CN4. CN4. What will be the contribution for CN4?
1 electrons. So for CN it will be 1.
For cyanide, okay, then total number of electron will be 16. Okay, then going to the next question. The geometry around the metal center in AgCN2 species is. Any idea about the geometry of silver complexes? It can be bent, it can be linear, it can be T-shape, and it can be trigonal planar. What will be the geometry of silver tetracyanide species? So
It will be bent structure.
no, actually for the silver complexes and gold complexes, when the silver Ag and gold Au in their plus 1 oxidation state. Okay, this is like very general information for the silver complexes and gold complexes, also for the copper complexes when they are in class 1 oxidation state. Okay, here the oxidation state of silver is
This one.
1. Okay, plus 1. So for the silver, copper and gold, that is for the coinage metal, for their plus 1 oxidation state, always remember it generally show the linear bonding mode. So metal complexes, if you see any metal complexes where the gold is, silver is or copper is in plus 1 oxidation state, generally it shows the linear complexes. So this thing, you can search any silver complexes, we will see different types of carbene complexes and heterocyclic carbene complexes. So we will see that silver complexes will be in class 1 oxidation state, it is always in linear. Some deviation may be of linear, means the whatever be the ligand, that is if L is our ligand, then Ag another L. So these AgL, this bonding is 180 degree. This bonding is 180 degree. So it can be deviate little bit from 180, but most of the cases this bonding is 180 degree. Okay, so this is the very general information for this coinage metal when they are in plus 1 oxidation state is showing the linear geometry. Okay, so the next question is the hybridization of metal bound carbon atom in sigma alkyl ligand is. What will be the hybrid sigma alkyl ligand? If we take an example of sigma alkyl ligand or metal complexes, it is
sp3.
what will be the hybridization of sigma alkyl complexes? Yes, so sigma alkyl complexes. So what is the general example is AmCl3. Okay, this is the general representation. So sigma alkyl or better ACr3. So this is the hybridization of this carbon is sp3. This is the sigma alkyl complexes. So the right answer will be option number C. Okay, very good. The hybridization of metal bound carbon atom in sigma aryl complexes. The same question is, but here we have our aryl ligand.
So it will be sp2.
Yes, the example is, any example? Can you give any example? Very common
The
example is,
metal bound to benzene.
yes, what it is called? Any example, particular example? pH, or what it is called?
Grignard.
Yes, so this is a metal bound complexes, that is a sigma aryl complexes. Okay, so this is, and I have another question, this is the last question. This question says the oxidative addition of CH3Cl to the complex L2IR iridium COBr occurs because it has electron rich, sorry, this is only electron not rich, this is electron, it has electron deficient center, it is coordinatically unsaturated, it is electronically unsaturated, it is coordinatically and electronically unsaturated. So what will be the correct answer? That is the oxidative addition. So here our main theme is oxidative addition. Oxidative addition we have discussed little bit in this week, mainly in the last lecture, that is the lecture 10. Week 2 lecture 10 we have discussed in this week very briefly the oxidative addition, and also we have discussed one exceptional of this oxidative addition for one complexes. It is possible to answer or not? Then I will discuss the answer.
Can you discuss the answer?
Okay. So oxidative addition is so in the last week part of this we have discussed the preparation and properties of sigma alkyl compound. Generally the preparation of sigma alkyl compound. So for the sigma alkyl compound, so that means we have an alkyl group, hybridization is sp3, that is the preparation of AmCr3 type compound in last lecture. So what is oxidative addition? Oxidative addition is when a metal has ligand, like I am just writing L, 4 ligand, let's for example, and its oxidation state is 1. So but here we can see that the metal can increase its oxidation state, that is from 1 to 3 when both are stable, and also metal can increase its coordination number. So here oxidation number is 1 and the coordination number is 4, right? But if metal can increase its oxidation number from 1 to, let's for example 3, that is the 2 electron oxidation, and it can increase its coordination number from 4 to 6, when metal with plus 3 oxidation state, and that is the higher oxidation state and with higher coordination number, and it is both are stable, that is this step and this step, metal is stable in both the step, then we can use that metal complexes like in its low valence to have the oxidative addition. Oxidative addition we will discuss in catalysis portion in more detail, but here for general information, so here we have our iridium complexes. Okay, so the two necessary condition for oxidative addition is metal should be, so that means it has plus 1 oxidation state, and also it has is less coordination number. So +1 oxidation state means it has more electron, so metal should be electron rich and it should have coordination number, less coordination number. So generally we say metal had coordinatively unsaturated, because unsaturation means it is below its saturation. 6 is the, we can say, for highest and most stable normal coordination number for octahedral complexes. If it is less than 6, so we can say it has coordinatively unsaturated, so it can also get 2 more ligand. Whereas the electron rich, that is electronically unsaturated. Electronically unsaturated generally described that it generally signifies that less than 18 valence electron, less than 18 valence electron for electronically unsaturation, whereas 18 valence electron is used to be the most stable. Let's going back to the question. Here we have the addition of CH3Cl to L2IrCOBr. This so we have IR CO Br L. So we can say that L is a neutral ligand. Okay, so L is neutral. Okay, then what is the oxidation state of iridium? Okay, so here the oxidation state of iridium is +1, and if L is a neutral 2 electron donor ligand, then the total valence electron will be 16 valence electron. So also it has a coordination number 4. That means this is less than 18 valence electron, also less than 6 coordination. So this is both electronically and coordinatively unsaturated. Okay, so for these types of complexes, and also these complexes electron rich, this complex is electron rich, having +1 oxidation state, having less than 18 valence electron, also coordination number less than 6. So these complex easily undergo the oxidative addition reaction. When CH3Cl, we have this complex undergo trans types of oxidative addition. That means that methyl and Cl attacked the metal center in trans fashion. So it will be CH3 same CO Br L and Cl. Okay, here here only bromide was negatively charged. Here bromide, chloride and this methyl has charge. So the overall is neutral. So the oxidation state of the iridium will be +3. So here the increase of oxidation state followed by the addition of CH3Cl, which called as oxidative addition. So for oxidative addition, two things we need to remember: metal should be in lower oxidation state, that means +1 +2, and that is less than 18 valence electron, and the coordination of the metal should be lower than 6, so that it can increase its coordination. So that means the metal center should be coordinatively unsaturated. These types of systems undergo oxidative addition reaction. So for the oxidative addition, we both need the electronically and coordinatively unsaturated. So back to the question again. So the first option say that metal has complex has electron deficient center. Is this correct? Because it is in +1 oxidation state. That's why it is electron rich center, not it is a electron deficient center. The second option said is it is coordinatively unsaturated. Yes, it is coordinated because here the coordination number is 4. So this option can be correct. It is electronically saturated. This is not unsaturated. This is called electronically saturated. This is not. It has total valence electron equal to 16 valence electron, which is not to the saturation. Saturation is means 18 valence electron. The option D is saying it is coordinatively and electronically unsaturated. So here option D will be correct answer. Is this clear, or any other question from this oxidative addition?
Yes, clear.
Huh? Any other question from this oxidative addition reaction?
No, sir.
Okay. So for the oxidative addition, metal should be electronically rich, electronically unsaturated, and coordination number should be less than 6. Electronically unsaturation means it has less than 18 valence electron, and coordinatively unsaturation means it has less number of coordinating ligand, that is less than 6 coordination. This is the general rule for the metal to undergo oxidative addition reaction. Sometime we may see that the metal complex have the 6 coordination number as well as the electronically deficient. Sometimes what happen, first this one of these, if we have the metal complexes with 6 number of ligand, 6 ligand, but then also the 18 valence electron is satisfying, then it also can undergo the oxidative addition reaction. But if it undergo oxidative addition reaction, the ligand which is already existing in the metal, like here the L should be replaced, or L should go out from the system to make the system coordinatically as well as electronically unsaturated. Okay. The exception for this, as I am discussing, the next is the coordinatically and electronically saturated system. To discuss this, another example is there where the metal undergo also oxidative addition reaction, like this: Cp, Co, cobalt, Co, PPH3. So what will be the total electron count for this molecule? It is very easy, na? Total valence electron count. Please tell me. Tell me the electronic configuration for the cobalt.
D7 4s2.
D7 4s2. That means this is a D9, total 9 electron plus CO 2 electron, and this one also 2. And what will be the contribution for this CP?
2 electrons.
Huh?
Sorry, 5 electrons, sir.
5. Total number of electron is 18.
18.
So these complexes have the 18 valence electron. That means it is electronically saturated. Okay. But these complexes also undergo the oxidative addition reaction in presence of methyl iodide. This is an exception of this what I have discussed previously. These complex also undergo these types of oxidative addition reaction. So here we have Cp, then our cobalt, CO, PPH3 and CH3. So what will be the charge for the cobalt now?
Plus 1.
Plus what will be the oxidation state for the cobalt? Okay, then how to calculate the oxidation state of any metal center? Let's say cobalt has X oxidation state and we have our Cp ligand. Cp ligand is always negative, Cp minus. So for the negative we have -1. Okay, and for the methyl group it is also negative, we have -1. Overall charge is positive, so we have +1. Forget about this I. This is the to balance the counter anion. So overall charge on this center is for +1. So X equal to 3. So the oxidation state of the metal is +3. Is this clear? How to calculate the oxidation state of any metal? Okay. So this is the 2 electron oxidation from the cobalt center. Here we also calculate the total number of valence electron. So for the cobalt it is again same, 9 electron plus Cp contributed 5 plus CO 2 plus PPH3 2 plus methyl 1, and we have our overall charge +1, that will be -1. Here again also we have 18 valence electron. This is a, here we can see that oxidative addition is happening on the metal center from cobalt 1 to cobalt 3. That means the oxidation is happening. Also the coordination number here also increasing because of the addition of methyl group, but the total number of valence electron remain the same in both the metal complexes. That's why this problem is very much important and I have pointed out this. Any other question from this weak content? Any other question? Do you have any other question from this? If you don't have any question, then I will discuss briefly in last few minutes the synthesis of the sigma alkyl compound. Briefly discuss it and then I will end this session. Okay. So sigma alkyl complexes can be prepared in different methods. First method is the very simple method, which is the metastasis reaction. The preparation of part sigma alkyl complexes sigma alkyl compound. So first method is the metastasis reaction. Here we have our any metal salt like M. We am writing a general representation MCl2 or MClX, better to say, and we have our very famous pregnant reagent like AR. AR is any aromatic compound or aliphatic compound, AR, Mg, Br. Then we will have the replacing the fluoride, we have AR, X, M. So this is a very representative or general expression for synthesis of metastasis reaction. Here we know that this AR has negatively charged delta negative as Grignard reagent. It will replaces all the labile halogen ligand or any labile group to have these metal bound aryl complexes. So this is the metastasis reaction is one of the very common reaction. A particular example is we have the ZR Cl4, we have 4 pH CH2 Mg Cl in ether. We are getting pH CH2 whole 4 because the 4 Cl was there, whole 4 ZR. Okay. So metastasis also we have the same kind of reaction called the transmetallation reaction, where this is also another the same like transmetallation. Here we can see that this is magnesium is a metal, also zirconium is another metal. So this ligand PHCH2 as a negative charge is replacing the fluoride. Another example is TiCl4. If we have Al2Me6, Al2Me6, that is the methyl group, is substituted by chloride. Substituted by this chloride, and we have our methyl TiCl3. So one methyl is substituted the one chloride. This is called somehow the transmetallation reaction. Another preparative method is the alkene insertion. For alkene insertion to form the sigma alkyl complexes or sigma alkyl complexes. For, for that we need a metal, any metal with hydride, plus we need any alkene like ethylene. So this will undergo reaction. This hydride will take part the addition with this alkene to give the metal alkyne complexes. So it will be CH2 CH3 if this is ethylene. So this is the general representation. So if we have the PT platinum hydride complex, here if we add the ethylene, then this hydride will be takes up this ethylene, react with this ethylene to give the platinum this CH2 CH3 platinum these complexes. This is the one of the method for synthesis the alkyl metal sigma alkyl complexes. Another reaction is the reduction reaction using the sodium. If we have Mn2CO10, these undergo reduction in presence of sodium amalgam NaHg. This sodium amalgam is a very useful reagent to reduce the metals because this has very electron rich system and it used to reduce the metal center to have Mn CO Na. This is the reduced metal center. Now this metal center can undergo the same kind of reaction to give Mn CO CH3 in presence of methyl iodide. This can also give this reaction. Another very important example is the acylation reaction for the synthesis of metal bound alkyl complexes. So here we have our Fe CO minus. In presence of acyl chloride, the Cl minus leaves and this acyl group H3CO group attached to the metal center. Now these acyl bound moiety, acyl bound moiety attached to the metal center is highly efficient to undergo the CO elimination in presence of photochemical condition to give the metal bound alkyl complex. This is a very good example of metal bound alkyl complexes. So this acyl moiety attached to this metal center is mm, prefers to eliminate the CO upon heating with or heating condition or the irradiation condition. Okay. So next is the oxidative addition, which I have already discussed for this question. These oxidative addition reaction for these iridium complexes, yes, this one, these iridium complexes is also a procedure for the synthesis of metal bound alkyl complexes. Then the last but not the least, the nucleophilic addition reaction. If we have any metal center Cp nickel with the ligand like the COD ligand, that is a cyclooctadiene ligand, bound to the nickel. Here this complex having the overall charge positive because nickel in +2 and this COD ligand is in neutral. Okay. Now because of the electron donation from this ethylenic double bond to the metal center, this double bond becomes electron deficient. Because of electron deficiency in this bond, this olefinic bond becomes highly activated. Activated means the olefins are generally electron rich species, but when the electrons is donating to the metal, it becomes electron deficient, and the deficient olefins we are called the activated olefins. These activated olefins in presence of any nucleophile like OCH3 minus undergo attack to this to give the nickel undergo this olefinic attack to give this hydrogen and hydrogen OCH3, and this hydrogen is bonded to the metal, and here Cp is as it is. So this, because of this addition of the OCH3, that is a nucleophile, is called the nucleophilic addition reaction. So nucleophilic addition reaction is also a very much well technique to get these metal bound metal alkyl complexes. So here we is very interesting thing to note that alkyl group or the olefins are generally electron rich species compared to the alkyl group, but when the alkyl group or olefins is bound to the metal, the electron density is somehow contributed to form the coordinated bond with the metal center. That's why the electron density on the carbon atom is somehow decreases. That is, these types of olefin is called the activated olefin, because of this deficiency of electron. Then any other nucleophile like OCH3 minus or any nucleophile can attack to this olefinic carbon atom to get the opening of this olefin bond to give these metal alkyl complexes. So today we have discussed so different types of metal complexes, that is the different class of metal complexes, class 1 and class 2 and the class 3 organometallic compound, and how they are differentiated based on the electron count and the reason behind the highest and the least number of electron having in different classes. So with the help of MO energy diagram, and after that we have also discussed the total valence electron count for the different system with different neutral also as well as anionic ligand. Then we have also discussed the uh, structures of some complexes like nickel complexes as well as the silver complexes. We came to know that copper, silver, gold in their class 1 oxidation state generally from generally from the generally from the linear complexes, and also sometimes we also observe the little bit deviation from this. And at last we have discussed some oxidative addition reaction as well as the synthetic procedures for these different sigma alkyl complexes. For that we have concluded this week 2, and last we have also discussed the activated olefin and how they are attacked by the nucleophile to form the metal alkyl complexes. I think this is enough for this. We have discussed most of the topic covered in week 2 content. I asked everyone okay. So I think this session will help you for better understanding the course content. If you have any doubt, any question regarding this session, please you can ask me during the session, or please post your doubts in the discussion forum questions we will try to answer as early as possible. And we have already completed the week second week of this course, and this is a, if anybody has any doubt you can post in the discussion forum. So hope you will enjoy this session in the upcoming days. If you have any suggestion, please fill the feedback form, or you can send, or you can ask directly to any improvement or anything if you need for this session, which will be beneficial for the learners. I will happy to help you in the upcoming days. Okay, thank you for attending this session, and this video will be uploaded in the and link will be shared in the subsequent days. Okay, hope see you all in the next week from Tuesday 6 to 8 p.m. Thank you.